Hey guys, today we're going to talk about one of my favorite topic in physics, which is called angular momentum. Not all of this will make sense to you right now, but let me just talk about angular momentum in general, then I'll explain everything. In physics, angular momentum is the rotational analog of linear momentum. It's an important physical quantity because it's a conserved quantity. The total angular momentum of a closed system remains constant. The angular momentum has both direction and magnitude, which makes it also a vector quantity, and both of which are conserved. Bicycles, motorcycles, flying discs, rifled boats, and gyroscopes owe their useful properties to the conservation of angular momentum. Conservation of angular momentum is why hurricanes form spirals and neutron stars have high rotational rates. In general, the conservation of possible motion of a system, but it does not uniquely determine it. So here we have a circle when we see an arrow. This basically means in what way it rotates. So basically anything that rotates it has angular momentum, and anything going in a straight line has linear momentum. So there can be two types of objects with angular momentum. First one is extended object. Extended object is something that rotates on itself, on its axis. For example, a neutron star rotating on its axis. Then we have a point object. The point object is something orbiting around something. For example, Earth orbiting around our sun, like that. So how do we find each of their and what do these letters means? So L stands for angular momentum, I stands for inertia, and this omega stands for angular velocity. What about for a point object? L stands for angular momentum, obviously, and you see this R, which probably already explained you, means radius. M stands for mass, and V stands for velocity. So here. Now let's solve problems relating to both of these objects. For a point object, like I said, a point object is something revolving around another object. So we have a radius, the distance between the center object and the orbiting object is about 0.28 meters. The mass of the orbiting object is 1.1 kilograms, and its velocity is 3.2 meters per second. So it's very simple to do this. Like I said, here in one of them we can see angular momentum equals radius multiplied by p, and in the other we can see radius multiplied mass and velocity. Well, it's actually both of these formulas are the same thing. Essentially, p is linear momentum, and to find linear momentum you need to multiply mass by velocity, which is right here. So instead you can just use this formula because it's exactly shows the simpler way, but for now we're gonna use this one. Okay, so we just plug in these formulas. We're gonna use this, so we multiply them, and at the end we get angular momentum of about, I'm sorry for my handwriting, it's my first or second time using the pen on the computer. So our final result is 0.99 kilograms. Kilograms. The hell is this? Sorry. Kilograms multiply meter squared. This is square. Sorry for the inconvenience. Per second. That's our angular momentum. Now let's move on to an extended object. Now we have an example of an extended object. So we need angular momentum times rotational inertia multiplied by angular velocity. We have here variables. Now, like I said, extended object is an object that rotates on its axis. I'm not gonna waste your time and do it by myself here because I've already done it. Here's the answer. This is the angular momentum. Let me explain something. You might know that neutron stars have more angular momentum than our sun. This is because they have more mass than our sun. You see, angular momentum is directly proportional to mass. Since the neutron star has more mass than our sun, its angular momentum is higher than that of our sun, so it spins much faster. And the spinning of a neutron star is an example of an extended object. And yeah, that's it for angular momentum. If you have any questions, ask. Thank you for listening.